So we're going to start off this week looking at section 6.4, which is the graphs of other trig functions besides sine and cosine. So we'll kind of go through the graph of tangent step by step, very slowly. But then when we do cotangent, we're not going to go through every detail as much because it's very, very similar. So we can write tangent as a fraction. Does anybody remember from the trig identities we talked about really briefly how you can write tangent as something over something?
Sine over cosine.
You can write it as sine over cosine. Now, let's think about the graph of cosine for a second. Cosine basically looks something like this. Does the graph of cosine ever hit 0? Does it ever cross the x-axis? Yes, it does. Well, if cosine x could equal 0, what would happen in this fraction? When you would have undefined. Okay, so what that means is you're going to have vertical asymptotes. Tangent has a vertical asymptote everywhere that the cosine is 0. Cotangent is basically the same thing, but it's flipped. Right? So tangent has a vertical asymptote everywhere the cosine is 0. So let's see if we can remember what these 2 points are. Right? So this is the beginning of the cycle, quarter of the way through, halfway, 3/4, and then all the way. Does anyone remember the x value?
Pi over 2.
Yep, pi over 2, or 90. And how about this one?
3 pi over 2.
3 pi over 2, or 270. So that's why if you try to type in the tangent of 90 on the calculator, we can just do it in radians. We'll do pi over 2. So we type in tangent of pi divided by 2. It says error. Okay, because what you're trying to do is this, which is the sine over the cosine. And cosine of pi over 2 is 0. So you can't divide by 0. All right, so we just said this. Tangent is, actually we did this part. There is a vertical asymptote when the cosine of x is 0. But when would this equal 0? What's the only way that a fraction can equal 0?
If the top is equal to 0.
The top is equal to 0. So tangent would equal 0 when the sine is equal to 0. Right? So this is our graph of cosine. Here's a graph of sine. What are the 2 spots where sine equals 0? The first 2 spots.
0 and pi.
0 and pi. So that means if you tried to take the tangent of pi, it should come out to 0. And it will. Tangent of pi is 0. Right? So if you break down tangent in terms of sine and cosine, you can kind of understand what's happening with the graph a little bit. All right. So knowing where the graph is going to cross the axis, knowing where tangent equals 0, and knowing where tangent has vertical asymptotes, is pretty much enough information to make a sketch. The only thing we might need is test a value on each side of the asymptote. So remember, when you get an asymptote, like if it was at 2, we check like 1.999 and like 2.001. When you check a value near an asymptote, what usually happens to your y value? It ends up where? Really high or really low? Yep, thank you. So anytime we're near a vertical asymptote, we're either going to be really high or really low. Let's try to make a graph of tangent and see what happens. So I wrote down the asymptotes you guys just told me. Pi over 2 is an asymptote. 3 pi over 2 is another asymptote. Okay? 5 pi over 2, 7 pi over 2, 9 pi. It's basically odd numbers of pi over 2. That's where your asymptotes are. Okay, so let's put in some asymptotes. All right, so we got pi over 2, 3 pi over 2, 5 pi over 2. That's enough. I mean, we could go negative pi over 2. And the zeros Okay, if we go back, the zeros of this function is where the top equals 0. That happens at 0, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. Okay? It's all the integer multiples of pi. So 0, pi, 2 pi, 3 pi, 4 pi. Now the only thing that's left to do is check a value near the asymptote. I'm going to check near pi over 2. All right. So let's pull up our graph. Type in tangent. And since pi over 2 is kind of a weird number to check what's near it, I'm just going to go like this. If I wanted to check a value just to the left of pi over 2, does that mean it's a little smaller or a little bigger? A little smaller. So what I'm going to do is I'm just going to take pi over 2 and make it just a little smaller, minus 0.0001. If you check a value just to the left, you're up at infinity. It's up very high. Now, where do you think you're going to end up if we check a value just to the right of negative pi over 2? Yeah, you will end up way down here. So, basically what your graph looks like is it stays very close, goes through there, and it looks just like that. That's the graph of tangent. That picture, I'll just do zoom 7. That picture will repeat itself over and over. And each time you see it repeating, that's another cycle. The one I drew is right here, right in the middle. But I could copy and paste that picture over and over. And that's the picture of tangent. Now, when we drew sine and cosine, if we didn't mess with the period, what was the period of sine or cosine? Anybody remember? 2 pi. Well, look at the cycle here. Negative pi over 2, that's like negative 90. Pi over 2 is positive 90. That's a full cycle from here to here. What's the difference between negative 90 and positive 90? 180. That's pi. So tangent has a naturally faster cycle than sine or cosine. Period of tangent, and I think we're going to write it down later on, is pi, if you don't mess with it at all. It repeats itself every 180. Okay. Now, what can be a little tricky is kind of saying, well, which asymptotes are in which cycle, right? Like, or if I said to you, how many asymptotes do you have per cycle? Anybody, just draw one more copy of that. Anyone think they know how many asymptotes are in each cycle of tangent? You gotta be careful because you can't count things twice. So, well, so if we said that, I'll put a black box around it. If we said that this one and this one belong to the same cycle, yeah, then we're saying that there's 2 per cycle. But then if you look at the next one, you'd have to say, well, wait, there's only 1. I can't say that this one belongs to it because I already said it belongs to something else. So yeah, there is only 1 asymptote per cycle. However you want to look at it, the one on the left or the one on the right, doesn't matter. But there's only 1 asymptote per cycle. Yep. Right. And that's why I put a box around this. So pi over 2, that's an asymptote within 1 period. 3 pi over 2, that's the next cycle down. Now, I'm not going to go through all the same detail for cotangent, but it's very similar. Okay? Cosine would have vertical asymptotes where the sine is 0, and it'll cross the x-axis where the cosine is 0. So basically, what happens between tangent and cotangent? All your asymptotes and all your intercepts switch. So, does everybody have that? I'm going to delete it so I can actually put tangent and cotangent right next to each other. All right. So look at tangent. Tangent's on the left. it has an intercept at 0. Look at cotangent. Now, 0 is an asymptote, and I've overloaded the computer. Thank you. Okay, so now let's look at pi over 2. In tangent, pi over 2 is an asymptote. In cotangent, pi over 2 is an intercept. So all the intercepts and asymptotes switch, because from tangent to cotangent, sine and cosine switched. That's really it. You could check a value on the calculator. You'll notice the curve is different. Tangent always has a positive slope to the curve. Cotangent always has a negative slope. You'll learn more about the slopes of curves if you do calculus, but that's the basic idea. Same idea with the asymptotes. There's only one per cycle in the cotangent graph. Okay. Any questions on that? So, this is what I said we'd write down later on. The period of tangent and cotangent is pi. The graphs of tangent and cotangent repeat themselves every 180 degrees. So, if I typed in, okay, in degrees, I'm doing this in degrees, tangent of 10. I should be able to type in tangent of what? And it would come out exactly the same. 190. Should be able to add 180 to that. And it does. Comes out exactly the same. So that idea, I'm summarizing right there. If you take the tangent of, I use 10. If you take the tangent of something, or the tangent of that something plus a multiple of 180, or a multiple of pi, it just depends if you're in radians or degrees, it comes out the same. That also works for cotangent. If you take the cotangent of something, or the cotangent of that something plus any multiple of the period, you will get the same thing. Okay, so what was the period of sine and cosine again? 2 pi. This is 1 pi. So its period, its natural period, is half of sine and cosine. Remember, n has to be an integer. So you can add multiples of pi or 180. You could add 180, 360, 540, 720. But you can't add a number that's in between. It's got to be a whole multiple of 180 or a whole integer multiple of pi. Add or subtract. Integers can be negative. You could add negative 4 pi, which is really just like subtracting 4 multiples of pi. All right, I've said this at least 10 times this year. The transformations with sine and cosine, or I'm sorry, tangent and cotangent, are exactly the same as the transformations we've done all year. So we're going to look at a problem with tangent and just see if you guys can identify which transformation is which. But since we've done them so many times now, we're not going to spend a whole day just on A and a whole day just on B. We'll just do them all at once. So what does A do? Horizontal shift. B? Horizontal stretch. C? Vertical stretch. And D? Vertical shift. Okay. So remember, horizontal shift, phase shift, same thing. We just call it a phase shift when it's with trig. Period change, that's your horizontal stretch. Amplitude change, that's your vertical stretch. And D is your vertical shift. It doesn't really have a special name just because it's trig. What if B or C was negative? You get a reflection, you get a flip. If B is negative, it's a horizontal flip. If C is negative, vertical flip. Okay, so any questions on what the different letters would do for the transformations. It's the same for cotangent. So I didn't write it again for cotangent. It's exactly the same. Okay, so we had a formula to find the period of sine and cosine. The formula was 2 pi over b, where b, just a reminder, b is the number in front of x. Well, tangent and cotangent, the formula is similar, but it's a little bit different. It's not 2 pi over b, it's 1 pi over b. In fact, the formula for 2 pi over b is the one you use most of the time. It works for sine, works for cosine, it works for secant, it works for cosecant. Tangent and cotangent are kind of the weird ones. They are the ones that have a special formula that's pi over b. Everything else, 2 pi over b. Okay. So now I'm going to show you, in general, how to find the asymptotes for a trig function. Okay, so when we have to make a sketch, that's the first thing. Because if you can get these asymptotes, then it gives you kind of boundaries of where to draw your picture. And this is going to apply to any trig function, not just tangent and cotangent, but you guys are going to see in a few minutes, secant and cosecant also have asymptotes. So this is how you find asymptotes in a trig function. First thing we have to do is just find the asymptotes in one cycle, or one period of the original. Now, I think if you're wondering, well, how can I remember what the asymptotes are in the original? Well, one way to do it, if you ask me off the top of my head, okay, what are the asymptotes for tangent? I don't remember. Okay, I would think of it like this. Then I'd say, okay, it's where cosine equals 0. So now in my head, I'm making a picture of where cosine equals 0. Oh, pi over 2, 3 pi over 2. There, those are your asymptotes. Right? But I think later on, I give you guys a chart. Yeah, I give you a summary of all the asymptotes for different trig functions, like where it is in the original, and then if you do a transformation, where does it end up? Right. So I've got them all for you right here as a summary. All right. So step one, you're going to have a table later on for this. So see table later in notes. Okay. Okay. So step two. Just because you know where the asymptotes are now doesn't mean that's where they're going to be if you do a transformation. So what do? Take the asymptote you found in step one and set it equal to the argument. So set the original asymptotes equal to the argument. Now remember, the argument is the stuff in the parentheses. Just to show you. This is the argument. Right there. The stuff inside the parentheses, is this the horizontal stuff or the vertical? It's the horizontal. The vertical stuff doesn't matter. Think about it. If you had a vertical asymptote and you shifted it up 3 units, would you be able to tell the difference? Like if you had this vertical asymptote, remember it goes up and down forever, and I shifted it up 3. No. Still goes up 3. I mean, it still goes up and down forever. Right? That's why the vertical shift, same with a vertical stretch. If something goes up and down forever, and you stretch it to be twice as tall, it still goes up and down. Okay? That's why all you have to worry about with vertical asymptotes is did you move it left or right? That's the important. All right. So you're going to use that table that we're going to have later on. Look up the original asymptote for whatever function you're doing. Set that equal to the argument and solve. Now, in general, all your asymptotes can be written just like this. Trig functions are periodic. That means they're very predictable. The same thing keeps happening over and over and over, forever. So once you find one asymptote, all you have to do is put plus the period times n, and that'll tell you where the next asymptote is. Because the asymptote will repeat every cycle at exactly the same spot and never changes. But the key is you have to find at least one asymptote to start. And then you can say, okay, that asymptote repeats forever every 180 degrees, or whatever the period is. Right, so we're gonna try a few examples of that. All right, so let's look at this one. So it says find the period, find a complete graph that shows 3 full cycles. So not something you have to do by hand. This is a calculator thing. Except the first part, y equals tan 2x. What's the formula to find the period of tangent or cotangent?
Pi over 2. I mean pi over b.
It's pi over b, which in this case is pi over 2. So what we've actually done here, have we done a stretch or a compression? We've compressed it. The normal cycle is pi. You've taken pi and made it half as big. That's a smaller number. That means your graph is going to cycle faster. So there's your period. Find a complete graph that shows 3 cycles. Okay. Now, there's a lot of ways to do it. If we can, it would be nice if we don't cut a cycle off, so we could have 3 nice connected curves. If you have like half of a curve and half of a curve and then 2 full ones, technically a half and a half is 1. But if we can, we try not to do that. So, my period for this graph is pi over 2. How long would 3 periods be? 3 pi over 2. It would be this triple. So what's one way that I can have a window 3 pi over 2 units wide? From what to what? Yeah?
From 0 to 3 pi over 2.
Yeah, that's one way to do it. And hopefully that doesn't cut anything off. But if we've done this right, remember tangent goes up and down forever, so I mean y min and y max, I just did -4 to 4. But let's see what we got. Okay, I know what's wrong. What's wrong here? Because this might happen to you. What about the mode? I'm in degrees. So if I want to do it in degrees, pi over 2 is 90. What's triple 90? 270. So I can do it in degrees if I want. I just need to set my x max at 270. And now I'm okay. If you're in radians, use 3 pi over 2. So we've got 3 cycles. We've got a half, a whole, and then a half. So technically that's okay. But can anybody, and it's actually easier to think about in degrees. We just did 0 to 270. Anyone think they could give me a window from what to what?
90 to 360.
All right. So we could do 90 to 360. What we're basically doing is we're shifting a little bit. Let's see if that works. 90 to 360. So that's still a width of 270 degrees. I think we shifted too much. So we shifted so much that we shifted.
45 degrees you need to go.
Yeah, so let's try shifting half that amount. And then 45 plus 270, 315. So now if I hit graph, I think, yes, I'm going to get 3 nice sections of tangent without cutting anything off half and half. Again, it's not super critical, but sometimes you might have to adjust your window to do things like that, to not cut things off. Right? Okay. So I'm going to put, you know what, I'll write the window by hand. So X min, we did 0. X max, that's what we did the first time. 0 to 270. Or the second time, we did 45 degrees, which is pi over 4, to 315, which is, pretty sure 45 times 7. So 7 pi over 4. I'll use radians from now on, but I was already in degrees for this one. Okay. Any question on that? Okay, it says, using the graphs below, identify which is the graph of 2 tangent x and 5 tangent x. So you basically have to know what the 2 and the 5 are doing. What are the 2 and the 5 doing there? What kind of transformation? They're vertical stretches. So the 5 is stretched vertically more than the 2. Which graph, the one on the left or the one on the right, is stretched more vertically? The left, right? Because the more you stretch out tangent, the straighter the curve starts to get. So this is 5 tan x, and this is 2 tan x. So a little bit different kind of transformation problem than what we're used to. I didn't ask you to list all the transformations here. I just wanted you to identify pictures. And there'll be one like that on the test. Okay. Any questions on that one? Okay. So let's take a look at secant and cosecant. Start with secant. Anyone remember how you can write secant as a fraction? Like if you wanted to type secant of 10 degrees in the calculator, this is how you'd have to type it.
1 over cosine.
1 over cosine. How about cosecant? Yep.
1 over sine.
1 over sine. Is cosine 0 at some point in the cycle? Yep. How about sine?
Yes.
Yep. So then secant and cosecant will have asymptotes. Secant will have asymptotes everywhere cosine is 0. Right? So if I think in my head, it's pi over 2, 3 pi over 2. Cosecant will have asymptotes where sine is 0. That's 0, pi, 2 pi, 3 pi, 4 pi. So here is your graphs of secant and cosecant. Right, so secant has asymptotes everywhere the cosine is 0. Those are the 2 I just said. Cosecant has asymptotes everywhere the sine is 0. 0, pi, 2 pi. All the integer multiples of pi. And you basically get like these U shapes and N shapes. How would you figure that out? You could just check a point to the left, check a point to the right of each asymptote, and you'd get values very high and very low. Also, if you think about sine, what's the range of sine? Normal sine.
0.
-1 to 1. Now, the range here is everything except that. It's everything from -1 and down, and 1 and up, it's like there's a gap in the middle. Okay? None of the values between -1 and 1 are covered. Okay? But that's what secant and cosecant look like. Now, I think the easiest thing, so you don't have to keep thinking about, okay, cosecant is 1 over sine, and then sine has 0. So you don't have to think about that. I'm going to give you the table. And then that'll help out a little bit. Also, the other thing, how many asymptotes per cycle here? 2. 2 asymptotes per cycle. This is a cycle in that box. A U-shape, a full U-shape, and a full N-shape. That's one cycle. And that U-shape and N-shape just repeats over and over. What you kind of have to decide in this box, if you call these asymptotes 1, 2, and 3, you have to decide out of the 1, the 2, and the 3, which ones belong to that box. They can't all belong to it, because then the next box over would be short, wouldn't have enough. So the way we think about it is there's 2 asymptotes per period. The way I think about it is the one on the left and the one in the middle. Those are the 2 that belong to the box. Asymptote 3 is going to be the one on the left in the next cycle. So two asymptotes per cycle. So let's kind of write down all the different asymptotes for each function we have. So tangent and cotangent only have 1 asymptote per cycle. I've given you the first one, or I've given you the asymptote very close to the origin. Okay? Remember, there's infinitely many. I could give you any one you want, but you just need one. Secant and cosecant have 2 asymptotes per cycle. So on the left are your originals. On the right is the new asymptote after you do the transformation. Now, these right here, I gave you guys directions earlier for how to find those. The x1s and x2, that's your new asymptote. It's basically where this asymptote moves to. That's where you set your asymptote equal to the argument and solve. Just to remind you that, right here. Step 2 is how you get everything that I circled right there. Set the original asymptote equal to the argument and solve. That'll give you the asymptote. Then put plus the period times n. And that represents the asymptote repeating forever. Okay, just don't forget secant and cosecant have two distinct asymptotes. If we worked with these graphs more, you'd probably have those memorized eventually, like you have the graph of sine and cosine more familiar. But we don't really work with them a ton doing this stuff. So I think the table is helpful. Question?
No.
Okay, does everyone have the table? All right. So I want to find the domain, the range, period, and the vertical asymptotes of secant. I'm going to come back to the domain. We'll do that after. Range. Well, kind of already gave that away to you, but if we wanted to graph secant, and you weren't sure what the range is, graphing it is the best way to tell. How do you type secant in on the calculator?
Second.
1 over cosine?
Yeah, 1 over cosine. Second would be inverse. we're not going to worry about that. Zoom 7. Now, to find the domain and range, you're looking at how high and low the graph goes. Well, does that graph go up forever?
Yes.
Yep.
Yes.
Does it go down forever?
Yes.
Yes. It does go down forever. You can zoom out, but you're just going to see that end shape going down further.
Oh.
The question is, does it hit everything in the middle?
No.
No. So what I would have to do is calculate a maximum for the end shape, and see how high does it go. And my guess, it goes as high as -1. And what do you think the minimum would be for the U shape?
Positive.
+1. So the range is all numbers except -1 and 1, right? Between, okay, not including, because it does hit those. So range -infinity up to and including -1, or from 1 including it, we'll hit it, to infinity. So that's your range. Okay, period. I told you that,
You have a close bracket.
yes, I should never have a closed bracket on -infinity. Thank you. I told you that the formula for the period is the same for sine, cosine, secant, and cosecant. Tangent and cotangent is the only one that has a different one. So what's the formula for the period of secant? Well, it's the same as, what's the formula for sine or cosine? 2 pi over b. Okay, so remember, sine, cosine, secant, cosecant. Formula is 2 pi over b to find the period. Tangent, cotangent, pi over b. Formula for period. Okay, so what's b in this case?
1.
1, it's just the basic secant 1x. So what's the period? 2 pi. It's 2 pi over 1, 2 pi over b, which is just 2 pi. Now, vertical asymptotes. Vertical asymptotes, or any vertical line, always starts out with what letter equals? X, just like I wrote in the table. It's always an x value. All right. So what we have to do is find a vertical asymptote in secant. Just one, any one you want. I gave you a suggestion in the table. Now I don't even remember what I wrote in the table, but if I had to do it quickly, I'd say, okay, 1 over cosine is secant, pi over 2. That's my first asymptote for secant. Pi over 2. The next one is 3 pi over 2. Okay? Thinking about where cosine has an x-intercept. All right. Now, it says to find the new one, we have to find what happens to these two asymptotes. Are we doing any transformations in this problem? No, then those two asymptotes are just going to stay right where they are. You're not doing anything to them. Okay. So, in terms of setting the original asymptote equal to the argument and solving, I can do that, but watch what happens. What's the argument in that problem? X. Right? So the argument is what you're plugging into the secant function. It's just x. The x is already by itself. So your vertical asymptote is x equals pi over 2 and x equals 3 pi over 2. Plus, we want to say how often this asymptote is going to repeat. how often it repeats is called the what? Period. This asymptote is going to reoccur every 2 pi radians forever. So the way you write it is 2 pi n. The bottom asymptote will reoccur also every 360 degrees, or 2 pi n. And that's how you write your asymptotes. Right. Any question on it? Now, I want to show you something because you may see something a little different, but it's basically the same idea. If we took pi over 2 and, yeah, let's do it like this. That's the same. Pi over 2 plus 2 pi over 1 times n. What's the common denominator between 1 and 2? 2. So let's go like this. Pi over 2 plus 4 pi over 2. Any question on that? Now, let's suppose n is 1. What's 4 pi over 2 times 1? Plus 1 pi over 2? 5 pi over 2. So here's the first one. Here's the next one of this first asymptote. Now let's look at the next one. N is 2. What's 4 pi over 2 times 2? So when you multiply by 2, remember it's really just like, just the 2 is in the top. So 4 pi over 2 times 2 is 8 pi over 2. What's 8 pi over 2 plus 1 pi over 2? That's the third asymptote, the third time it repeats for this first one. What do you think the next one would be? 13 pi over 2. Okay. And so on. Now, let's look at the bottom. We had 3 pi over 2 plus, same thing, 2 pi n. The first one is 3 pi over 2. The next one, what's 4 pi over 2 times 1? 4 pi over 2 plus 3 pi over 2. 7 pi over 2. Let's do one more, I think you'll see the pattern. 4 pi over 2 times 2. Plus 3 pi over 2. 11 pi over 2. So that asymptote repeats 3, 7, 11. Right? Those are the numbers in the numerator. The other asymptote, 1, 5, 9, 13. So basically, your asymptotes, if you kind of combine that all together, you could say both of these at the same time. Can anybody kind of summarize all the numbers in that list? Every multiple of pi over 2? Which ones? Odd multiples. So what you really could say here for your asymptotes, if you didn't want to write this fancy equation, is all odd multiples of pi over 2. The way we did it, we described the first asymptote separately from the second. But you don't have to do it that way. You could say all odd multiples of pi over 2. So you might see something like that and be like, how the heck did they get all odd multiples of pi over 2? It's because they wrote out the two formulas and looked for a pattern and said, oh, 1 pi over 2, 3 pi over 2, 5 pi, 7 pi, 9 pi, 11 pi. Oh, it's odd numbers with pi over 2. Any question on that? Sure. I generally just leave it as the two separate equations, and that's fine. But in calculus, you may see in the book, like they say all odd multiples of pi over 2. I'm like, how'd they get that? That's how they got it. Okay, let's try cosecant. Oh wait, did I do the domain?
No.
I didn't do the domain. Well, the domain is everything except the vertical asymptotes. Okay, the vertical asymptotes are what you are not allowed to plug in. So that's what I usually just write for the domain. All reals except the vertical asymptotes. You can plug in any number you want except numbers that are odd multiples of pi over 2. That'd be a really fancy way to say it, if you figured that out. You can plug in any number that's not an odd multiple of pi over 2. That's why I saved the domain for last, because once you get the asymptotes, you get the domain. Okay, domain. Let's go to the range first. What's the range of cosecant? It's on the right.
The same.
Same as secant. Yep, it's exactly the same thing. It's almost like it's just been shifted a little bit. But other than that, it's the same. Okay, so range negative infinity to negative 1, including, or 1 to infinity. What else? Domain range, period. What's my formula for the period of cosecant? 2 pi over b, right there. Secant, secant, 2 pi over b. What's b? 1. So period 2 pi. You got to find the period before you do the asymptotes, because the asymptotes have at the end of it plus the period times n to show the repetition. Okay, vertical asymptote. Think of cosecant, 1 over sine. Think of where sine crosses the x-axis. What are the first 2 spots?
0
and pi. So x equals 0, which I guess you don't really need. And that asymptote is going to repeat how often? Every 2 pi n. And the other one is going to repeat? Same thing. Now, this one's even easier to combine into one statement. If you let n equal 1 here, what's 2 pi times 1? 2 pi plus 0. What's 2 pi times 2? 4 pi. 2 pi times 3? 6 pi. Now, let's look at the bottom one. 2 pi times 1? 2 pi plus pi? 3 pi. 2 pi times 2?
4 pi.
4 pi plus pi?
5 pi.
5 pi. 7 pi. So, how could you describe all your asymptotes here? All multiples of pi. Nice, very simple, very elegant way to say it. Every multiple of pi. So your domain is every number that's not a multiple of pi. So I could say all reals except vertical asymptotes. Shouldn't be an apostrophe. Vertical asymptotes. Okay. Questions on domain, range, period, or asymptotes? So that's what I usually write for domain. All reals except the VAs. No vertical asymptotes. Okay, find the period and asymptotes and show 2 full cycles on the calculator. So again, you just write down your window for that. Okay. What's the period of cosecant 3x? 2 pi over b, so in this case. Yep, you could write 2/3 pi, 2 pi over 3, same thing. All right, asymptotes. How many asymptotes per cycle of a cosecant function? 2. Now, cosecant, you can look at the chart, but I usually just think of it in my head. Cosecant is 1 over sine. Where does sine cross the x-axis? First 2 times.
0, 5.
Okay. 0. And where else? Pi. Now, I'm not writing those down yet. I'm putting them off to the side. Because have we done a transformation here?
Yes.
Yes, then those asymptotes are not going to stay where they are. They're going to move. How do we figure out where they move? Step 2. Take the original asymptotes that you just gave me, 0 and pi, set them equal to the argument and solve. Those are going to be the 2 numbers that we want. So, let's go back here. What is my argument here? 3. 3x. Set the first asymptote equal to 3x. Set the second asymptote equal to 3x. When you solve those equations, that'll tell you where the first asymptote goes and where the second one goes. How do you solve both of those? Yeah. So the first asymptote doesn't really move because it's at 0. And no matter how you stretch or compress the number 0, 0 is 0. Where does the second asymptote end up? Pi over 3. Your graph compressed by a factor of 3. That means this asymptote is now compressed by a factor of 3. It doesn't move over as much. So 0, pi over 3. How often are each of those asymptotes going to repeat? 2 pi over 3. Now, oh, and don't forget your n. What's 2 pi over 3 times 1? 2 pi over 3 times 2. And let's do one more, times 3. What I'm trying to do is look for a pattern to see if I could say this nicer. There's nothing wrong with this, but there might be a nicer way. 2 pi over 3 times 1. 2 pi over 3 plus 1 pi over 3. Yeah, I'm going to write it as 3 pi over 3. The next one is 5 pi over 3. 7 pi over 3. How could you describe all your asymptotes here? What is it? All multiples of pi over 3. Yep, all multiples of pi over 3. 2 pi over 3, 3 pi over 3, 4 pi, 5 pi, 6 pi, 7 pi. So in words, you could say all multiples of pi over 3. As an equation, you could say basically this. That represents all multiples of pi over 3. Plug in a 1, 2, 3, 4. Any question how I got this? It's okay if you leave it like this, but I think most anything you do that gets more advanced than this, they're not going to write it as 2 separate ones. They're going to put it all together as 1. Okay, I would not take points off if you leave it as 2. It's okay. But it's all multiples of pi over 3. So, domain they didn't ask for. Okay, so my period is 2 pi over 3. How wide of a window do I need to show 2 cycles? 4 pi over 3. So what's a min and a max that I could do? Yeah, I'm not worried about cutting it off. These graphs are getting a little fancy, so let's just go 0 to 4 pi over 3. And we're graphing cosecant 3x. That's not 1 over cosine, it's 1 over sine. Let's try it. We should have 2 U shapes and 2 N shapes to show 2 cycles. That's 1 cycle. That's 1.5, 1 3/4, 2. 2 cycles. Any question on that? Okay, so a little tricky because you got to remember you did a transformation. So set each argument equal to set each asymptote equal to the argument and solve. And those are the 2 numbers you put here and here. Obviously, if one of your asymptotes was 0, it doesn't make a big difference. Okay, so the last thing we'll look at is how to solve an equation on the calculator. Now, think about something like this. If I wanted to know where the sine function hits a half, how high and low does the sine function normally go? 1 and -1. So it's definitely going to hit a half. How many times does it hit 1/2? Infinitely many. All you have to do is find all of the answers in 1 cycle. here, and here. How often are those two answers going to repeat? In general, every cycle, whatever the cycle is. So this answer is going to occur again 1 cycle later. This answer occurs again 1 cycle later. This answer, 1 more cycle. This answer, 1 more cycle. So just find the 2 answers that you need in 1 cycle, and then put plus the period times n. So, point is, if you have a trig function and there's 1 solution, then there's infinite solutions, because that solution will repeat every cycle. So, the idea is just what I showed you. Find 1 solution, and then put plus the period times n. In the problem I showed you, there were 2 solutions per cycle. There's 2. There could be 1, there could be 2, there could be 3. It depends. Depends on what you're graphing. In general, we really don't get to more than like 2 or 3 until you graph complicated functions. By a complicated function, I mean a function that mixes sine, cosine in the same problem. Like maybe cosine 4x minus sine 2x. Now you're going to have a graph that's really different. Okay, but for now, we're not mixing trig functions yet. Because then once you mix trig functions, then you have to figure out how do you find the period of a mixed problem. It's easy, but we will do that later on. Not this chapter. Okay, so let's look at last 2 examples. Find all solutions to cosecant x equals negative 1.6. So, all means that I want to see plus the period times n. Degrees or radians is technically fine. Maybe let's do example 6 in radians, and then we'll do example 7 in degrees. All right, we're not worried about how to solve this algebraically right now. So, what's going to be the strategy to get this done on here?
Break it in half.
Okay.
It's like each half equal to y.
Okay, so what would you put in y1?
Cosecant x.
And how would you take it? 1 over sine. Yep. Right, and what would you put in y2? Negative 1.6. Now, if we hit zoom 7, you're going to end up seeing lots of solutions. Now, just let it go. What we really want to do is focus on the solutions in 1 cycle. So what I usually do is, I don't even set the window so I can see more than 1 cycle, because then it's just more stuff to confuse me. What's the formula for the period of cosecant?
2 pi over b.
And what's b in this case?
1.
1. So the period of cosecant is what? It's just 0 to 2 pi. Let's not even look at more than that. If you look at more than that, you're just confusing yourself with other stuff. Let's just look at 1 cycle. Find all the answers in that cycle, and then those answers will repeat off the screen forever. Okay, how am I going to find the 2 solutions here? Second, calc, intersect. Okay, now I'm not sure where I am, but if I look, my x is 2.9, so I'm probably on the top part of the U shape. If I keep pressing to the right, eventually I'll come back to the bottom. Okay, so the first answer is 3.82. Plus, what do you put on the end of it to show how often it repeats?
2 pi n.
2 pi n. So if you wanted to know what's the next time this answer is going to occur, add 2 pi to that number. What's the next time? Add 4 pi. The next time after that, add 6 pi. You can keep finding. Okay, and second calc, intersect. Do it one more time. And should be good. That answer occurs, let's see, 5.61. And how often does that one repeat? Every 2 pi n. Now, I keep saying add 2 pi. You can subtract 2 pi. You can find the answers going back to the left off the screen, just as much as you can find the ones to the right. And that's it. Those are your 2 answers. Any questions on that one? Okay, so that one was in radians. So I did radians. Let's do this one in degrees, just to practice. Okay, tangent x equals 2.5. So same idea to start. Tan x, 2.5. What's the formula for the period of tangent?
Pi over b.
So pi over b is in radians. What's pi? 180. So it's 180 over b. What's b in this case? 1. What's 180 divided by 1?
180.
So let's go 0 to 180. If you look at more than that, you're just confusing yourself. Just focus on one cycle. Clearly done something wrong, and I know what I did.
Forgot to switch.
I didn't switch the mode. So radians, you're only supposed to look at 0 to, let's see, radians, that'd be 0 to 3.14. Well, I went all the way to 180. So make sure you change your mode. Okay, I'm just going to stop. Change your mode to degrees, and now you should be good. But that's good, because that might happen to you, and now you know how to fix it. So looks like we broke a cycle in half. That's okay. Doesn't matter. As long as you get one full cycle. How many answers per cycle? Just one. Second, calc, intersect. Shouldn't matter where I put the cursor. It should grab it, I think. No. Did I do intersect? Second, calc, intersect. Let's try a point on the blue, point on the red, and a guess. Okay, so 68.20 degrees. You do need the degree label on that, because it's a degree, it's not a radian. Plus, how often does that repeat?
180.
Every 180. Yeah. I guess it's, yeah, how you could write that. Every 180 degrees. Any questions on that? Okay. So that wraps up everything that we're going to do with graph. Tomorrow we're going to look at solving right triangles with opposite adjacent hypotenuse, like Secant, Pythagorean theorem. Should be pretty straightforward. Okay, so that's the homework for tonight on 352. Okay, don't forget, if you still have anything to make up, which I think everybody in here most are good, but if you still have a test to take, any tests have to be done by Thursday. Okay, you would know if you have a test to take because I updated your progress reports and I filled in zeros. Check X2 and see if you need to take a test.